Oh, I didn't see you there. No tricks, nothing fancy. Let's just do a little bit of similar triangles. Okay, here's the plan. I'm gonna put an object in here, and we prefer to use seafoam green for objects. My object will be right there, and it will be that tall, and there'll be a couple rays that we could draw. I could draw you, I guess I could draw you the M ray and the C ray, but ultimately we'll get our, see, foam green. Yeah, check this out. There will be our image. Let's see. I don't remember what color is what. In fact, no, I could check it out. We could do this. We can do this. The C ray is usually blue. So I'm going to draw the C ray. It comes straight from the object through C and goes to the image. Here we are. There's our C ray. And I don't want to clutter anything else out right here because I'm going to do some cool stuff. But this is some angle we could define to be phi, let's say. Sorry, that's a theta. I want this angle to be phi, and I want this angle also to be phi because of some property of geometry whose name I have forgotten. Also, there's, you think I can do this on the same thing? Yeah, let's just do it. There's, oh no, that was the wrong color already. Well, I'll switch colors again and go purple for my M ray. The M ray is planning to hit the mirror, boom, and bounce back out this direction, and you will see that I have two pairs of similar triangles, and everything is cool. This angle of incidence is the same as the angle of reflection because it's hitting where it looks like a planar mirror right there. And so theta is theta and phi is phi, and we've got ourselves two similar triangles. I'm not going to shade them because I think that would just make it really complicated. Remember, we can label some distances here. We're going to say that this distance is, well, here's the line of action. We're going to say that this distance is the distance of the object from there to there, and this distance is the distance of the image from there to there. Distance of the image, distance of the object, and this distance right here, I guess we'll have to define that distance to be ara, which is the radius of the spherical mirror that we propose possibly made this thing happen. Now it's time for us to make some statements first. I'd like you to look at the blue pair of triangles. No, just kidding. Let's start by looking at this purple pair of triangles because it's a little bit simpler. I want you to notice that this is the height of the object, and this right here is the height of the image. And of course, the height of the image is a negative number when I actually get down to it. And then I'm going to get myself an equation, and that equation is going to say that, I guess I'm thinking about something about like tangents. This distance right here is the distance of the object, and that distance is the height of the object. So if I say opposite over adjacent, that's going to be the tangent of theta. That'll be h naught over d naught. That will be the same as this similar triangle, hi, but not regular hi, the opposite of hi, divided by the distance to the image, which is this di right here, and that's a positive number, so that's cool. And we've got ho do is negative hi di, which is kind of fun to say, but it might be even more fun. Ho di hi. Wow, that is fun. Now, I'm going to change it around just a little bit. So instead, it says h object divided by negative h image. See, I'm going to do, what do they call that? Cross multiplication and simplification? I don't know. I'm doing something fun. And then I'm going to say this is do over di. Ho over hi is do over di. Di. I don't know. Yeah, have a good time. Pronounce it as you like. But my point is, this will be an equation that we will carry over to the next page, and that'll be really fun. In fact, I'm going to rip this equation out. You don't even see this equation anymore. Get ready. It's going to be gone. Because it's so portable. A little portable. Gone! Anyway, regardless, that equation is gone. So that's what my M ray did for me. It came down the middle and gave me two similar triangles. Now it's time for things to get a little bit more funky because I want to draw your attention to these two triangles, and this is messier. I'm shading this triangle in yellow, and I'm shading that triangle in yellow, and I want to try to figure out what these distances are. Like this distance right here. Oh boy. That distance must be do minus r. do minus r. What about this distance right here? It's a little bit smaller, and it seems to be Oh man, r minus di, you see that? It's r minus di. Sure it is. This is r minus di. And I can set up a very similar equation. I say if I know this over that, then I know this over that because they're the same. They're going to be the tangent of that phi angle right there. And since phi is the same, its tangent must be the same. Okay, so I say HO over DO minus RA is HI over RA minus DI. I don't even want to try to pronounce that. Yuck. But I can solve it for ho over negative. Wait a second. This should be minus. This should be negative because this is downward. So we got a minus sign right there. Very important. Don't lose your minus signs. I'm going to solve this for HO over negative HI, and I'll find that to be, well, that's just DO minus RA divided by RA minus DI. Look, there's some symmetry here. You're definitely seeing some symmetry. I'm going to put a box around this guy right here, and then we're going to go to the next page. Say goodbye to these nice, beautiful triangles. But notice that this is where we got it. We were focusing on the M ray and on the C ray, and we found two similar triangles that relate HO and HI. And you'll find that they always do. They're not always so pretty. That's why I drew them like this, because they're pretty. Of course I did. But they can always be done. This is going to be a general conclusion. And I will rip out this second equation and do some algebra on the next page. And because it's algebra, it should be in pink. Notice that these two equations each have the same left side. I will equate them because they're equations. I'm going to say D object over D image is D object minus RA divided by RA minus D image. You might think that it all reduces to nothing, but it doesn't, and I'll show you how we know. All I have done is I've set these two equations equal to each other. Watch. Equals that one, and then I worked with the right sides, and that's what I've got over here. So my next step with this equation, sorry the battery died there, is to multiply the left side so that I get it to be equal to 1, because I think 1 is fun. And I'm going to do DI over DO to clean that up, and I'll put that on the right side because algebra is always good and fair and just and right and such. So we'll put an equal sign down here and we'll stay in purple because it's a little bit more fun. We say 1 is, now instead of writing the same thing, I'm going to change it just a little bit so that it's worth my time to do this step. And I'm going to make my parentheses slightly different over here. We'll go orange, and I'm going to do instead 1 over DO divided by 1 over DI. Maybe you see why I'm about to do that, but we'll have the next line in orange, and our plan is to get, well, we've got 1, and then we've got, ooh, this is 1 minus R over DO, and I divide that by, well, this is going to be R over DI, and then I'm supposed to subtract, wait a second, DI over DI, that's just 1 again, and then I want to clean up the right side some more. So I'm going to go gray with this particular one, and I want to multiply it by the denominator, which is R over DI minus 1. And I have to do that to the other side because algebra is always good and true and just and right. And I'll divide by DI, and I'll subtract 1 right here. And then on the next line, I get 1 minus R over D object equals R over D image minus 1. Are you thinking that those 1s are going to cancel out? What do you think? Really? Let's move some terms around and figure this out. I say that I get, well, certainly over on the left side, I've still got R over DI. I'm not going to move that away because it's pretty. I want this one over here, and that's going to be plus R over D object. But over here, I've just got, wait, what do I have? Figured out. Okay, 2. Now, my next step is to take this equation, and you know that I don't like those r's in the numerator right there. Did you notice that? I'm going to put it in parentheses and multiply by 1 over r, and I'm going to divide by r over there, and I'm going up and to the left. Okay, now we've got, wait a second, all of those r's are going to cancel out on the left-hand side. I've got 1 over di plus 1 over do is 2 divided by r. It's time to take a little breather. Do you remember this whole thing, this whole, oh, what was it? We're going to go green with this one. The whole focal length, what the heck it is? Well, it is 1/2 r, or if you're feeling fancy, it's r divided by 2. Wait, r divided by 2? Well, this is 2 divided by r. That's r divided by 2 divided by r. Are you saying that this is 1 over, are you saying that we've got 1 over d image plus 1 over the object is 1 over the f. No, sorry, there's no d right there. This is the mirror equation. Can you deal with it? Hope so. Oh, by the way, this equation is extremely powerful and you no longer have to do any ray tracing. Somebody might still ask you to do ray tracing, but you can laugh at them because now you can solve any problem. Of course, you'll have to remember when the distance of the image is negative and the distance of the object is negative and the focal length is negative. These things can't happen. Good luck. Maybe you should stick with your ray tracing.